So it's my pleasure to introduce our first speaker, who is the mastermind of this whole HiPACC enterprise. And that's Professor Joel Primack, who is an expert on many aspects of particle astrophysics and cosmology, essentially the father of the cold dark matter model, and a great proponent of why we're all here, trying to link evolution of structure in the universe to fundamental particle physics and nuclear physics.
Thanks, George. I don't need it because they already mic'd me up. Incidentally, the lectures are being recorded by the UCSD TV station. You see their camera in the back. And also, Elizabeth Lovegrove, who's sitting next to our host, Mike Norman, who runs the San Diego Supercomputer Center. So Elizabeth is going to collect PDFs of the slides after each lecture, and we're going to try to post them very quickly. The videos are being posted directly to YouTube right after each lecture. So we want to make all this available to you as the students as quickly as possible so you can look at the lecture slides, especially in the afternoons when you're going to be logging on to the powerful local supercomputer, Gordon, and learning how to use some of the latest codes. So my talk is going to be about modeling galaxy formation and chemical evolution. The first thing I'm going to do is briefly tell you a little bit about the High-Performance Astro Computing Center, which started in 2010. This is now the 5th summer school that we've had, the second one here at UC San Diego at the San Diego Supercomputer Center. And I just wanted to give you a little background on what we're doing. We're up for renewal. There's an opportunity to get 4 more years of funding, and so one of my main jobs in the next couple of weeks is to finish the proposal for that, and then hope that we persuade the powers that be to keep allowing events like the summer school. Then I'm going to very briefly summarize the basics of our modern cosmology, lambda CDM, and then talk about simulations of 2 different types. Very large-scale simulations where we just use dark matter, but keep high resolution and keep track of all the details of the simulations. And one of the things we do with these large-scale cosmological simulations, like the Bolshoi one that my group did, is to do halo abundance matching and age matching, and then compare to observations with semi-analytic models, among other things. And crucial here is I'm going to summarize in a few slides the key data on galactic chemical evolution. Then these are dark matter simulations, but if you want to really understand galaxies, you've got to simulate galaxies at very high resolution with every physics, every bit of physics included. So these are hydrodynamical simulations. They include star formation, feedback, and also, of course, the formation and evolution of the black holes and other internal structures in the galaxies, and especially including the feedback from them. And what I'm going to do is show you some of the current situation where we have now, thanks to the astronauts having installed Wide Field Camera 3 on Space Telescope in 2009, we now can see galaxies out to redshift 3 in rest frame visible light. So we have now hundreds of thousands of images in many wavelengths of these forming galaxies. And so now the challenge is to make simulations that are sufficiently similar to these observations that we can begin to understand what's really happening. And there are a number of surprises, things that we hadn't really anticipated a few years ago, that are turning out to be absolutely critical to galaxy formation. So I wanted to show you a little of that. There's 11 different teams around the world that are now comparing their high-resolution hydro simulations, starting from the same initial conditions and using exactly the same tools to analyze them. And that's the Agora project. So I'll briefly tell you about that, and then summarize very briefly by talking about some of the challenges we face. So the HiPACC website, many of you have probably seen it because you've logged on to fill out the application for the summer school. But in addition to the summer school, we sponsor many conferences, and we always put the slides and often the videos online. So there's a lot of wonderful stuff here. including a recent conference at Lawrence Berkeley Laboratory in March on the future of astrocomputing toward exascale, and at UC Irvine in February, and that was called Near Field, Deep Field Connections. So both analyzing data on the earliest galaxies and also the dwarf galaxies nearby, which probably haven't done much since the early epoch of the universe. In addition to that, we have a series of what are called Astro shorts, which are written by Trudy Bell. Trudy, would you? Actually, there's Trudy, right over there. Trudy's also taking photographs. She'll be here through Thursday of this week. So every month rather, roughly, she writes a one-page popular article about some recent development in astrophysics involving the UC campuses or the 3 Department of Energy laboratories, Lawrence Berkeley Lab, Livermore Lab, and Los Alamos Lab that we're affiliated with. And there's an archive of all of those. We also are collecting press releases from all the UC campuses and labs in 3 areas: astrophysics and astrocomputing, also big data and basically new techniques in computing and data analysis, and all kinds of outreach talks in these areas. And those are 3 different categories. And what Trudy's doing is writing brief summaries of each one with an appropriate image so that you can very quickly see what's happening in the University of California. And we've been doing that now for a while, so you can get a pretty good picture of what's happening in the whole UC system. One of the purposes of the University of California High-Performance Astrocomputing Center is to make the university act more like a collection of interacting campuses and labs rather than a bunch of competing and not very much interacting campuses and labs. Taken together, the University of California is the world's premier research university by any standard, Nobel Prizes, any other standard of citations. But we don't usually compare all the campuses and labs together. If we did, of course, we're a monster. But we have to start acting more like an organism and less like a bunch of individual parts. So that's one of the things that we try to do. We have representatives on all the campuses except for UC San Francisco, which is just a medical school. There's a small number of staff that really make the whole thing work. And I've been helped greatly by Peter Nugent at Lawrence Berkeley Lab and Mike Norman here at San Diego, who've been the sort of Southern California coordinators. We have been funding, in addition to the schools and conferences, also readily available travel grants to facilitate interaction between the campuses. And we've done many of these, and a lot of new collaborations have resulted across the UC system. For example, Davis and Irvine, or a number of other ones across Southern to Northern California. And we've also allowed up to $10,000 of matching funds for computational astronomy equipment. For example, the ability to handle large amounts of data. So half a terabyte of RAM or a terabyte of RAM on a single system, or big storage systems. And also a visualization lab. So these are the summer schools that we've had each summer on galaxy simulations, computational explosive astrophysics, which we're revisiting this summer because there's, of course, been all kinds of new things. And this one didn't do much about neutrinos. That was at Berkeley and Lawrence Berkeley Lab. Astroinformatics and astrophysical data mining here at UC San Diego. At UCSC last summer, star and planet formation. And this summer, as you know, neutrino and nuclear astrophysics. Now, this is the latest, most colorful version of the ultra deep field, now using Wide Field Camera 3's ultraviolet capability, as well as its infrared capability, in addition to the advanced camera for surveys. Very pretty. But it's misleading, because all the light you see comes from half of 1% of what's actually out there. About 4.5% is baryons, but only about 10% of the baryons actually are stars or are gas clouds lit up by stars. So 99.5% of the universe is invisible. this is the visible part, represented symbolically, of course, using the Great Seal of the United States. This says the new order of the ages, and I think modern cosmology really is that. Now, out of the Big Bang come hydrogen and helium. Almost all the helium in the universe was there at 10 minutes after the Big Bang. Only a little bit of extra is made by all the fusion in all the stars. The first stars are just made of that hydrogen and helium, and then they make all the other atoms, the whole rest of the periodic table. And of course, that's one of the topics this week and next week that's nuclear astrophysics. And the I in this symbolic representation, so this top part represents all the other visible atoms. That's about 2% of that 0.5%. So in other words, 100th of 1% is oxygen, the most common metal, then carbon, nitrogen, and all the other ones, iron and so forth. We intelligent creatures could only be made of those heavy elements. If all you've got is hydrogen and helium, you've got no interesting chemistry. What about the rest of the 99.5%? Notice that this is sitting on the ground. You can think of it as in a gigantic hidden pyramid. So there's that 4% of invisible atoms, not stars, not lit up by stars, mostly out in between the galaxies or the distant reaches of the galaxy halos. Most of the mass in the universe is cold dark matter. I proposed with Heinz Pagels back in 1982 that the natural explanation of this is that it's the lightest supersymmetric partner particle, which Gary Steigman and Mike Turner called a WIMP, a weakly interacting massive particle. I wish I was clever enough to come up with that clever name. Of course, we don't know if that's what it is. But we're getting much more sensitive, and this wonderful announcement a week ago by the Department of Energy and the National Science Foundation that they're going to expand the Large Underground Xenon, or LUX detector, currently operating at the Homestake Gold Mine in Lead, South Dakota, from 1/3 of a ton of liquid xenon to 8 tons, making it 100 times more sensitive, greatly increasing the fiducial volume, which will make it, again, the most sensitive dark matter detector. That will be sufficiently sensitive that they will either see the dark matter of a WIMP type or else rule that out. And then dark energy, the most mysterious part of the picture, it makes the universe expand more rapidly. It behaves just like a cosmological constant as far as we can tell, but it might be more interesting. It might change in space or time. And there are several big projects underway to try to discover if the dark energy is just a cosmological constant or something more interesting. So here's a more fanciful version of that same pyramid. Imagine the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But we don't see the ocean and we don't see the ships. All we see are the beacons on the tops of the tallest masts of the biggest ships. Those are the galaxies. So dark matter ships in a dark energy ocean, lambda CDM, or since that is our modern picture, we should have a popular name for it. So I suggest the double dark theory, dark matter, dark energy. Now, this is the key idea of cold dark matter. This is from a paper that George Blumenthal and I presented back in 1983 as we were working the theory out. And then these are from the Nature paper in 1984 that laid out the whole dark matter theory, compared it with observations, and said that it looks like it might be right. So the idea is that fluctuations enter the horizon at the same amplitude, or very close to the same amplitude. That's a so-called Zeldovich spectrum of fluctuations. So on the vertical axis is the amplitude of the fluctuations, delta rho over rho, the log of that. And they come in a little over 10 to the minus 5. And now this is scale factor. The scale factor, 1 over 1 plus redshift, is our clock that says how much the universe has expanded. And scale factor, by definition, is 1 today. So log of it is 0. Once the fluctuations are in the matter-dominated universe, then they grow as fast as they can, if they're adiabatic fluctuations, everything fluctuating together. And that means they're growing linearly in scale factor. So that's these straight lines all parallel. But if they enter in the radiation-dominated early universe, the general rule is that the only structure, the only component that grows rapidly is the dominant, the gravitationally dominant component. Here, radiation is the gravitationally dominant component. That's photons, neutrinos, and at earlier epochs, particles like electrons that are moving relativistically. But the ordinary matter, the dark matter, which presumably is some kind of heavy WIMP, hardly grows at all, only grows logarithmically until matter dominates. And so all the fluctuations that enter, 10 to the 6 solar masses, 10 to the 9 solar masses, 10 to the 12 solar masses, that enter during the radiation-dominated universe show little relative growth between them. You see this piling up. If you just read off the amplitude today, you get this cold dark matter spectrum. This is 10 to the 18 solar masses. 10 to the 22 solar masses is the total amount inside the horizon today. And so you get this characteristic shape, falling more rapidly on large scales, see the big separations, but only a little growth on small scales as you go to smaller and smaller scales. So smaller scales enter slightly earlier and have a little bit more growth, but only logarithmically more. So we derived this back in '83, and this was the basis of the whole model where we started to do semi-analytic modeling and predicting what galaxies would look like and so on. So this was the first paper that really explained why galaxies exist, why they have the masses they do, and also their distribution in space. Well, that's the data, which we now have assembled. This is exactly that same plot. It's basically delta rho over rho on different length, different mass scales, covering 11 orders of magnitude. And you just couldn't ask for better agreement. Smaller than galaxies, galaxies, clusters of galaxies, all the way up to the horizon. So the cold dark matter theory is a fantastic success. Cold dark matter plus the assumption of inflation also predicted the pattern of the fluctuations in the cosmic microwave background. And this is the data from the Planck satellite, which is better on small angular scales than the WMAP NASA satellite data because Planck had better resolution. Every point is an independent measurement, and there's no discrepancy whatsoever with the predictions of the theory. When we first made these predictions, people laughed and said, surely you don't expect all these wiggles are really going to be there in the data. And we said, look, we just work out the theory. That's what it predicts. And sure enough, and the same theory also predicts the cross-correlation of temperature and polarization, and polarization and polarization. The Planck folks are going to release the polarization data and their full analysis of it, they say, this October. This is the angular correlation function, basically. So the theory is clearly right on the large scales. Now, as I said, we're going to discuss two different kinds of simulations. The dark matter simulations that we do on large scales and the hydrodynamic simulations that we do on smaller scales. Astronomers give us snapshots. They show us what a galaxy looked like when the light left it millions or billions of years ago. The job of theorists is to make movies, either literally or metaphorically, and I'll show you some literal movies, of course. And the idea is that we are supposed to make theories that produce snapshots that agree with the observations and also explain how the material in the galaxies or the distribution of galaxies is behaving to produce these snapshots. So this is from a simulation called Aquarius, run by Volker Springel and collaborators in Europe, of the halo of a galaxy the size of the Milky Way. And this is how big a Milky Way galaxy actually is, about 100,000 light years across. So the halo is at least 10 times bigger. That means the volume that halo occupies is 1,000 times bigger than the volume of the visible galaxy. So galaxies, remember, are just the tip of the iceberg, or pyramid. And there's an enormous amount of invisible stuff. How does this fit in to the large-scale structure of the universe? Something like this. So this is a slice of the Bolshoi simulation. Bolshoi was run with nearly 10 billion particles with a kiloparsec resolution and it's 250 H inverse megaparsecs across. So almost 10 to the 6th factor in each of the 3 linear dimensions, which is currently the best we can do, given processor speed and so forth. And anyway, it hardly makes any sense to go better than a kiloparsec if you're just doing pure dark matter. So we, of course, have to evolve the simulation, and we store many time steps, typically 200 time steps, complete data on all the particles and velocities. And you see all of these are expanded to the full final size. We call that working in co-moving coordinates. And you see how the matter flows out of these regions that are destined to become cosmic voids and into the filaments and along the filaments to where they cross, and those are where the clusters form. So let's look at a cluster, a place where these filaments cross, and let's just look at 1,000th of the Bolshoi simulation. So just roughly 100 megaparsecs, 100 million light years on a side. So what you see is that dark matter halos form these where the filaments cross, you get these big halos that host groups and a big cluster of galaxies. A cluster has between 20 or 30 and hundreds of galaxies the size of the Milky Way, and if you count small galaxies, many thousands of galaxies. You'll notice that mass is quite elongated. That's true in the simulation. Dark matter halos for galaxies like the Milky Way have a ratio short to long axis of about 0.6, but for clusters, about 0.4, so it's 2.5 to 1. We can make statistical predictions regarding the distribution of galaxies of different luminosity, and I'll show you, they are extremely accurate. Moreover, we predicted back in 2004 that the distribution would be different at high redshift, and as the data has come in, our predictions were exactly confirmed. So the theory really works. Now, this is just a still of that forming halo. What I want to do is show you how we keep track of all the substructures, all the dark matter halos, each of which hosts a galaxy, that ends up just in this single central dark matter halo. So every one of these little blobs is a dark matter halo. As we catch it in the simulation, we show it, and then they merge and merge to make these bigger dark matter halos. And those continue to merge. You'll notice that there's an inflow along here, and along here. That's typical. We usually have 3, or you have a single filament with a side filament coming in. So we do this for every single halo at every time step. We first find every dark matter halo, and then we form what we call the merger tree. So we see how halos at a given time step become halos at the next time step and the next time step and so on. And then all of that data is made publicly available. We've made it available since 2011, and many groups have continued to use it. So this was a popular article that was in July 2012, Sky and Telescope, and this is one of these visualizations, and that's actually my silhouette in front of the hyperwall at NASA Ames. So incidentally, the Planck data suggests a somewhat different cosmology, and we have run the entire Planck cosmology. We did it on the Bolshoi scale with the same resolution, and then we've done it on successively larger scales with poorer resolution. And all of that data is now becoming available on the multi-dark website, MULTIDARK website at the Astrophysics Institute in Potsdam. Now you have to compare simulations like this and observations, this is the Sloan Digital Sky Survey, in a statistical way with sub-halo abundance matching. My former student, Risa Wexler, likes this somewhat modest way of describing it, because it is a sham. So what we do is we just assign dark matter halos to have galaxies in them of a certain stellar mass or luminosity. And we do it basically by rank ordering the halos by their internal velocity, their maximum internal velocity, and rank ordering the galaxies by their stellar mass, and then aligning them, assigning stellar masses to dark matter halos so that you have about the right number density. That's how we do it. That's called subhalo abundance matching. And an alternative method, which does that, but then does one more thing, was proposed by Heron and Watson last year, and they've now written a series of papers on this, and I'm now working with them. And they added one more wrinkle, and the fact that this actually works is one more proof that the universe really knows about the dark matter halos. So, as I said, we do abundance matching, and we assign luminosity or stellar mass to halos, and then we can work out their correlation functions. And this is correlation functions of very bright galaxies, fainter, fainter, and you just couldn't ask for a better agreement than that. This isn't any fake thing. This is what actually comes out. And then the other game that these guys played was, okay, let's take this one step further. Let's suppose that the rate at which the dark matter halo is accreting, which is different, is not just given by the mass of the halo. There's one more parameter. Risa Wexler showed this in her dissertation with me in 2002, that the dark matter mass of a halo is the mass today, the mass at any redshift, is the mass today times e to the minus alpha times redshift. And of course, that works at any redshift. Compare any redshift to any other redshift. So it's just basically like charging a capacitor. But alpha, the e to the minus alpha z, that's different for each halo. You have to find that from the dark matter merger tree. So that's what Heron and Watson did, and they said, well, the halos that are still accreting today, they're also bringing in some gas with the dark matter, so they should have some recent star formation and therefore should be blue, because, of course, the young stars that don't live very long, supernova, the O stars, those are very blue, very ultraviolet dominated. And then an old population with little new star formation, that's red. And so galaxies are bimodal. There's the reds and the blues with only a few in between. And they have quite different correlation functions. The reds are highly correlated, the blues are not. And just using this simple trick to assign now star formation rates or colors to galaxies gives this amazing agreement. And in many other ways, it really seems to know what's going on. It's producing an amazing phenomenon I don't have time to go into called galactic conformity that was discovered in the observations 6 or 8 years ago. But it's now actually exactly what this predicts. So one more proof that the dark matter is really there and controlling the way galaxies form. Here's another rather nice one. So the Milky Way has two big, bright satellite galaxies, the Large and Small Magellanic Cloud. The most active star-forming region is the Tarantula Nebula in the nearby universe in the Large Magellanic Cloud. So what's the probability that a galaxy as bright as the Milky Way will have companions as bright as the Large and Small Magellanic Clouds? Well, the Bolshoi simulation has adequate resolution to find everything that would be as big and bright as these clouds. And so we have enormous statistics. We have 10 million dark matter halos that can host a galaxy at every redshift once the thing gets going. Fortunately, the Sloan Digital Sky Survey, Stripe 82, went deep enough that we have about 3,000 Milky Way analogs that we can actually get statistics on. So we count how many of those have halos, have subhalos that would host the Large or Small Magellanic Cloud. And we do the same thing in the enormous Bolshoi simulation. And the results are, the Bolshoi simulation with these tiny little error bars is in red. That's the number of satellites, up to 5. And this is the data from the Sloan Digital Sky Survey. And every case agrees within observational errors. So we predict that it's about 10% of galaxies the mass of the Milky Way will have two bright satellites like the Large and Small Magellanic Clouds. And that's quite consistent with the observations. About 65% have no bright satellites. Okay, now I was supposed to talk about chemical evolution, so I want to summarize some of the key data on galactic chemical evolution. So this is from a famous paper by Tremonti et al. Analyzing the Sloan data, and this is the evolution tracked by the most common, most abundant metal. Everything heavier than hydrogen and helium we call metals, of course, namely oxygen. And what you see is that you've got increase of metallicity with a fairly big dispersion, and increasing dispersion at low stellar masses. This is the stellar mass. Up to about 3 times 10 to the 10 solar masses of metals, about half of what the Milky Way has. Solar masses of stars, I meant to say. And then the metallicity basically is flat. There isn't much increase. A little bit, but not much. If you track this down to even smaller masses, using the local group dwarf galaxies, what you see is that there's a remarkably regular pattern, except for maybe a flattening at the very lowest end. Namely, the metallicity seems to go as the stellar mass to the 0.4 power. And I want to emphasize that these are the same plot. This is simply extending it down to still lower masses. And this is where at 3 times 10 to the 10, this is where the Sloan data says the metallicity starts to flatten out. So what's the explanation for this? Well, the obvious explanation was proposed right after the cold dark matter theory was invented in our 1984 paper, in a now very famous paper by Avishai Deckel and Joe Silk, 1986. And Avishai told me that's what made him a believer in cold dark matter. So what they did is they said that supernova feedback is going to produce winds of approximately 100 kilometers per second. So that's going to correspond to dark matter halos that will host about 3 times 10 to the 10 solar masses of stars. And that's the basic reason that below that, you get more and more blowout because of the supernovae, because you can translate this into about 100 kilometers a second, about 50 kilometers a second. That's the that's the small Magellanic Cloud. And then these little dwarfs, 10 kilometers a second. And then the little dwarfs, as Evan Kirby's going to tell you, based on his remarkable analysis of the pixels of the spectra, they retain only 1% or 2% of the metals that they generate. Whereas the massive galaxies retain a large fraction of the metals they generate. So that's the basic story. And that has to get incorporated into any realistic model. So this is the evolution of the chemical abundance in the Milky Way. And the game is that we use the magnesium to iron to trace the time evolution. The idea is that the type 2 core collapse supernovae occur quite rapidly on a time scale of a few million years. Whereas the type 1a white dwarf supernovae occur over a much longer period, hundreds of millions of years to billions of years. So, and of course, the alpha elements like magnesium are generated in the core collapse supernovae. It also generates some iron, but not so much. And then a lot more iron is generated in the type 1As. So we can use magnesium to iron as a star formation time scale. And the normalization, the magnesium to iron ratio, is going to depend on the initial mass function, which we now know, thanks to the work of Charlie Conroy and Peter van Dokkum and others, does depend on environment, with the dense regions like the centers of the biggest galaxies in the Virgo cluster and the Coma cluster having bottom-heavy IMS with a lot more low-mass stars, super saltpeter, and the small galaxies being top-heavy, having more than their share of high-mass stars. So the IMF has to be taken into account to do a good job. The Milky Way IMF does appear to be close to the standard Chabrier or Krupa. And then also it depends on the yield tables. And in other words, how much of different elements come out in different mass supernovae with different metallicities and so forth. And that's something that really has to be improved. There's quite a lot of literature that doesn't agree all that well. And so that's one of the challenges to nuclear astrophysics. Now, then you see that once you get up to Fe over h of -1, this is always compared to the sun when you put the brackets. It's log compared to the sun. Then you see this fall off. And so this is now the production of much more iron. And so type 1a start making a major contribution there. And the Ni, this shape here, is determined by the star formation history and the time delay distribution, delay time distribution for the type 1a's. So those are the crucial parameters. And the delay time distribution is still not very well understood. There's clearly a prompt component and a delayed component. And I'll show you in a minute that different models tend to give somewhat similar results in doing this chemical evolution. So that's the story on the Milky Way. Now, there's this remarkable series of papers by Jenny Graves where she analyzed data from the Sloan Digital Sky Survey, thousands, tens of thousands of galaxies. This is what's called the fundamental plane of early type galaxies, elliptical and lenticular galaxies. So the face-on fundamental plane, the horizontal axis is the velocity dispersion, and the vertical axis is the effective radius that includes half the light. And what you see is that age, this is old, this is young, and metallicity, higher, lower, depend primarily on sigma, and these lines are almost vertical in radius. So radius is not a key parameter. It's determined by the velocity dispersion. So that's true for early type galaxies, that is the spheroidal dominated galaxies. It's also to some extent true for disk galaxies. So one of the ways that we try to track this is using semi-analytic models. So we put a galaxy in every halo on a big simulation like the Bolshoi simulation. When halos merge, the galaxies will have a tendency to merge. There's a process called dynamical friction that will bring this galaxy inside its halo that's now merged to merge with this galaxy. That often causes a starburst, feeds the supermassive black hole. Lots of new star formation, eject metals, and heat the surrounding medium. And what typically happens is that the galaxy then becomes old, red, and dead, surrounded by some hot gas. We have to follow the observed relationship of star formation rate to the density of material, of star forming material. And so all the simulations and these models follow that. Semi-analytic models basically do simulations that can handle hundreds of thousands or millions of galaxies by sphericalizing everything. So the key parameter is always the radius. Now, the most important thing that we know is that the dark matter, from cold dark matter, is that the dark matter halo distribution, that's the red curve, doesn't have this steep bend that the galaxies do. This is the abundance of galaxies as a function of their luminosity or mass. And so something has to be decreasing the abundance of galaxies compared to dark matter halos at the low mass end and also at the high mass end. At the low mass end, I've already explained to you, supernovae are the obvious culprit. At the high mass end, these galaxies are sufficiently massive, there's no more new star formation. So you can't depend on star formation to impede star formation. It must be something else. And the obvious culprit is the supermassive black hole, because supermassive black holes are roughly 1,000 times more efficient at converting mass to energy than stars are. Only the inner 10% or so of the mass in a star fuses, except, of course, for M dwarfs, where they actually convect and can live for 1 trillion years. But for normal massive stars, that's not the case. And, of course, all you get out is a few MeV per GeV. And so the efficiency is less than 10 to the minus 3, whereas a supermassive black hole can convert mass to light with an efficiency approaching 1. For a rotating massive black hole, it could be 40%. So the result is that we get, this is the color magnitude diagram, red up here, blue down here, and very few galaxies in here in what we call the grain valley between red and blue. The most massive galaxies today are red. And that's naturally produced by these semi-analytic models. So the models involve lots and lots of interesting features. And you have to include dissipation in gas-rich galaxy mergers. And you also have to include spheroid formation by disk instability. And I'll tell you more about that in a couple of minutes. So we have many regularities of elliptical galaxies and spiral galaxies. And the semi-analytic model is reproducing all of them. So this is our latest paper on this. And the thing that was interesting is that at high redshift, everything's small. The universe hasn't expanded very much. The dark matter halos are small. The disks are small. If disks merge, they make small spheroids. And the observers say, yes, the galaxies at high redshift are very compact, very dense. That, we feared, would build in a radius, age, and metallicity relation, which is not seen in the observations of the nearby galaxies. So we were absolutely delighted that when we put the whole thing together and ran it, what we found was that we had basically the same dependence, namely strong dependence on sigma, very little dependence on radius, in the semi-analytic model, both for galaxy age and galaxy metallicity, as in the observations. So it works. Age and metallicity depend mainly on velocity dispersion, not radius. So that paper that I just mentioned has just been accepted for publication in monthly notices, and we're going to post the accepted version, which is very similar to the version that's on the archive now, next week. This is another very recent paper by our main competitor. There's a dozen teams around the world that do semi-analytic modeling, but I think our group and we call ours the Santa Cruz model, and this is the Munich model. They've been the originators and creators, especially Guinevere Kaufman and Simon White, husband and wife team. So they've tracked 11 elements. Here's 8 of them. This is their delay time distributions. So there's 3 different delay time distributions that they've used. A peak, and a long delay, a power law, and a Gaussian model. I can see it, but I think you probably can't. That's a Gaussian. But anyway, it turns out that there isn't too much difference in the results, although they say that the best model for matching the wide range of observational data should include a power law delay time distribution. So that's this one. But if you actually read the paper, it's not that sensitive. Okay, there's just a little time left for me to tell you about what we're learning from these extremely high-resolution hydrodynamical simulations. So let me get right into that. There's basically 2 approaches. There are people who do fairly big volumes. The latest, the record holder now, is 100 H-inverse megaparsecs. So that's 1/16 the volume of Bolshoi, but they've done it with hydro. And that's called the Illustris simulation. And then earlier simulations were called the Overwhelmingly Large Simulations, a modest title. That's led by Joop Shea in the Netherlands. And so the advantages are you simulate lots and lots of galaxies, and you study the interactions of the galaxies with the circumgalactic medium and the intergalactic medium. The disadvantages, we learn little about how galaxies themselves evolve. And in fact, what Illustris did is it disabled the beautiful Arepo hydrodynamics inside the galaxies. And it basically did semi-analytic modeling. It just forced the galaxies to look like the galaxies we see. The high-resolution simulations, so these are like a kiloparsec. These are like a few tens of parsecs. So these are basically 100 times higher resolution in each of the 3 axes. So 1,000,000 times more computer work. So these are much more expensive. But it's possible to compare in detail with galaxy images and spectra, discover how galaxies evolve, what the morphological drivers are that give you the shapes of galaxies and clumps, and what makes galaxies stop forming stars. But it's hard to run statistical samples. And so the best approach uses the simulation insights, puts them into the semi-analytic models, and then the semi-analytic models can evolve hundreds of thousands or millions of galaxies. So that's the current state of the art. And using the ART simulation suite, which is what my team, working with Anatoly Klipin and Avishai Dekel, has been doing, and the Agara simulation comparison project is going to be a great expansion of involving many groups. So this has been the typical problem in doing low-resolution simulations. Namely, that instead of having a disk galaxy where you've got most of the material in the disk having the angular momentum compared to what you need for circular support be 1, that's what a real disk galaxy looks like, with just a little bit here that represents the bulge. Instead, you get something that looks like this. There's no galaxy in the universe that looks like that. This would be a rotating elliptical galaxy. And elliptical galaxies don't rotate that fast. So there's nothing like that. Well, that was 2009. So Cecilia Scanopiecco led this comparison project with 13 different simulations. None of the high-res ones. These are all low-res, half a kiloparsec or so. And every blessed one of them was a failure. There wasn't one that looks like a real galaxy. This was published just 2 years ago. Meanwhile, in 2011, the ERIS simulation, led by Javiera Goodes in her thesis work with Piero Madao at Santa Cruz, for the first time, they did an adequate resolution simulation of a spiral galaxy, and it looked just like a spiral galaxy, just the way a spiral galaxy should look, in every respect, pretty much. And it was the first try. It's just that they used adequate resolution. So it seems clear that we now can do it. We just need to bite the bullet and spend the computer time, which is typically 100,000 to 1 million core hours per simulation. Fortunately, we now can get that kind of time on big machines. So this is how these things work. On large scales, this is 320 kiloparsecs. Material flows in along filaments, usually 3, and the galaxy forms right in there. This is what a simulation looks like. White stars, blue gas. You'll see that the color code changes as the simulation evolves. Once the thing starts rotating, it keeps rotating, even though it's perturbed a bit by continuous merging. So we store typically currently 500 time steps as these things evolve, and we store complete information. We've run about 100 of these simulations, going up to several times 10 to the 12, several times 10 to the 13 solar masses. That would be a massive elliptical. So we just take a big box simulation, and we just zoom in on some more or less randomly selected, evenly spread in log mass or log circular velocity. And these lower mass ones, the Milky Way would be around here. This is its mass at redshift 1. These lower mass ones we've run now twice. We were persuaded that it's really important to include radiation feedback. This is the nearby Rosette Nebula, and these are O stars. And you see that they're clearing out the gas. There's these pillars of creation that are protecting regions where planets are presumably forming. But the gas is being pushed away by the tremendous radiation from these O stars. No supernova has yet gone off, and probably won't for another 1,000,000 years or 2. And it's very important that you clear out this region, because then when the supernova goes off, it doesn't just immediately dissipate all its energy as heat in supersonic turbulence, but instead it has time to develop a Sedov-Taylor vast wave, which then can entrain material and produce the galactic fountains and such that we're familiar with. And so we have to include this in our simulations, but it makes no point in doing that unless you've got resolution of about 10 parsecs, which is what you need to resolve these giant molecular clouds. So that's why it's absolutely critical to have the high resolution. So we do that. We put in the pressure. There's 2 groups that have now published papers on this. The other group is led by Phil Hopkins at Caltech, including Dushan Karas as the second author here at UC San Diego. And we're using different implementations, different codes, and getting somewhat similar results. It makes a big difference, actually, in these are exactly the same initial conditions. This is with the radiative feedback, this is without. And this shows the stellar distribution. And what we noticed is that the stellar distributions tend to be elongated for the lower mass galaxies. These are pictures that we made with the sunrise code. This is the same initial conditions, number 27 of 35, at the same time steps. And this is face on. Notice how elongated this is. Now we're doing the detailed statistics. So radiation feedback makes galaxies more elongated. And a paper has just been accepted and is either on the archive or will shortly be on the archive. First author is Arjen van der Velde. So this is our Candel's group. And guess what? It's true. That's how galaxies really are. Now, in order to make these realistic-looking images, you've got to take the dust into account. It's tremendously important. It absorbs as much as 90% of the short wavelength light and then re-radiates it at long wavelengths. So we developed, this is my former student, Patrick Janssen, this code that's now become standard for doing this. And we put all kinds of tricks in. So this is 1,000 times more efficient than most other codes. And it produces very detailed spectra. You can see how the ultraviolet without dust is highly absorbed, and edge on, there's essentially no ultraviolet left, very, very red. And then that energy is being re-radiated at long wavelengths. The wide field camera 3 infrared capability, this is H-band 1600 nanometers, is what's allowing us to see the old stellar population. We used to just be able to see the young stars. Now we can see all the stars. So that makes a tremendous difference. And this is the biggest project in the history of Hubble Space Telescope. It just ended as far as the data collection phase, and we have till the end of 2015 to finish our papers on it. So if we didn't include dust, these are negative images. So what's black is actually bright white. We would get these clumps much too bright. Notice how clumpy the real galaxies are. Real galaxies are very clumpy. Our simulations are very clumpy. The clumps form through violent disk instabilities. This shows how the dust dims the center, but also scatters light. So it makes things rounder and dimmer. So this is what these galaxies would look like if we could see them close up. This is at redshift 2.1, so that's about 11 billion years ago, 12 billion years ago. And this is the same galaxy face on, edge on. You can see a merger is about to take place. And then we automatically make these images as Hubble Space Telescope would see them. These are two of the bands from the infrared bands from Wide Field Camera 3. These are standard visual bands from, this is near infrared and middle of the optical spectrum. Same thing for this. So now I'm going to show you exactly the same time step, but in the simulation with radiative feedback. Notice how even the face-on is quite elongated. And in all cases, you always see these clumps. And these are not giant molecular clouds. Giant molecular clouds are 10 to the 6 solar masses, sort of at the high mass end. These things are 10 to 8 to 10 to the 9 solar masses. There's nothing like that in the nearby universe. These clumps are really quite amazing. And they're ubiquitous. At least half of star-forming galaxies at these redshifts, which is where most of the star formation is occurring, are clumpy. This is the comparison face on, no radiated feedback with radiated feedback. Now, the other thing you notice is there's just a lot less star formation. A standard problem with the simulations is we're overproducing stars at high redshift. And there wouldn't be enough gas left to produce stars at redshift 2, and the galaxies would be too red at redshift 2. But putting in the radiated feedback solves that problem. So this is the thing that we've been missing up until now because we couldn't do it unless we had adequate resolution. And of course, we had to understand how to do it.
Principal feedback from radiation pressure just on star formation just to get rid of gas?
It doesn't get rid of the gas. It just impedes the star formation. It doesn't push it very far. And the amount of energy that's released by the radiation is 20 times the energy that the supernovae will eventually release. If you leave that out and you try to account for it by boosting the supernova energy output, which is what we used to do, dumb, crazy, doesn't work. It's not physics. This works.
Does it skew the IMF at all? Because you're basically just increasing the...
We're checking that now. of course, actually, we're not checking that because we put in an IMF. But now what we can do is we can follow the yields and see if the time evolution is in better agreement. So there's this article that just came out in the June issue of Sky and Telescope where we summarized what we've learned so far from the Candles survey. It's online. You can download it from HiPACC. And it's just on the right-hand side of the front page. And this shows a bunch of these images that we generated, and these are the Hubble images to compare with. So this is this paper that's just been accepted, Vandervelde et al. So they classify galaxies as elongated, that's prolate, spheroidal, or disky. And so this is mass, lower mass, 10 to the 9 to 10 to the 9.5 solar masses of stars, up to 10 to the 3 times 10 to the 9 to 10 to the 10, 10 to the 10 to 3 times 10 to the 10, 3 times 10 to the 10 and up. And you see at the massive end, they're spheroidal. The lower masses at low redshift are disky. But look at this. The majority of these galaxies are elongated. And now we're doing the statistics on our radiative feedback galaxies, but it's clearly basically doing this, doing what the observations show. What does a galaxy of that stellar mass look like today? Well, there's the third brightest galaxy in the local group, the Triangulum galaxy, M33. That's our typical galaxy, a nice disk galaxy today. Incidentally, this is not elongated. We're seeing it at an inclination of about 55 degrees. So we see these clumps. These are the gas. These are the sunrise images. Semiotic models, remember, actually, I didn't make this point sufficiently strongly. A majority of galactic spheroids formed by violently unstable disks forming clumps that drive gas and stars to the galactic center rather than by mergers. And so these are observations, theory, observation, theory. This is the age. And so what this shows you is these are galaxy mergers. These are the clumps that form in the disk and then migrate into the center as they get older, age increasing this way. And there's evidence from observations that it really does look like that. And I don't have time to go into this, but basically these are a direct comparison of observations and simulations, and we're now building the statistics on that. We have hundreds of thousands of observations, hundreds of thousands of simulated images, and it's a complicated process to compare them, but we're doing it now by machine. This was done by having 30,000 images visually inspected by a minimum of 3 and usually 5 different astronomers. So it's taken 2 years to collect data in a relatively small number. This is the project where we're comparing 11 different simulations, 50 institutions in 8 countries. Currently, 108 astrophysicists are part of this. And we're getting excellent support from the National Energy Research Scientific Computing Center, NERSC, at Lawrence Berkeley Laboratory, which is providing the computer power and initially 100 terabytes of storage, and then they'll up that and they'll make that archival so that we can have a workspace. So common initial conditions, common analysis platform. It's the YT platform that was developed by Matthew Turk, first in his PhD work with Tom Abel at Stanford, then as a postdoc here with Mike Norman at San Diego, then at Columbia, and he's just accepted a job at the University of Illinois at Urbana-Champaign, which is a permanent job. This shows the same simulation, but if you look carefully, it's not exactly the same. This is 9 different codes. Initial conditions, we're going to do 8 different cases, 10 to the 10 to 10 to the 13 solar masses, each one twice with quiet and complex merging histories. We're going to include, as much as possible, exactly the same physics. It'll only be the subgrid physics that's different in the different codes. And we're going to compare them all based on the same platform, this YT platform, which can read and interpret every code. And we've developed instantaneous visualization software that'll become available to this whole group because we have to have the hardware to support it. So this is using the latest NVIDIA cards that have 12 gigs of RAM and 3,000 cores. And doing that, we can put the data, the output from YT, on one of these cards, and then instantly produce stereo high-definition images, 30 frames a second, just like that. No delay whatsoever. and you can change anything on the fly. We've got an HTML5 GUI, so you've got all kinds of widgets. You can change where you are. You can change your thresholds. You can change your color code, and it responds just like that. And we will pump the stuff out at internet speed. We've routinely got 10 or 20 frames per second across the country or the world. So all of this is being supported at NERSC. Thank you, NERSC, at Lawrence Berkeley Laboratory. And thank you. I think I finished in just an hour. Trudy, you had a question?
Yes. If many of the galaxies are prolate, what would cause part of the galaxy to go this way and this way? Why would they be prolate?
It's a good question, and I could speculate, but the advantage of the simulations is that everything is there. We can figure out exactly what's going on. So one of the questions I'm asking, and we have a bunch of students working on this at Santa Cruz this summer, is to track the shape and how it is connected to the angular momentum axis and also to the larger shape of the dark matter halo. And we'll have all the answers, I think, in a month or so.
When speaking of tracking it with the dark matter halo, I had essentially the exact same question regarding the halos. You said that they tend to all be these
Elongated, yes. Right. Triaxial ellipsoids.
Okay, and so do you know why that is yet?
Oh, yeah, sure. The key paper on that is the PhD dissertation by Brandon Allgood with me, published in 2006. And also Bepi Torman in Italy wrote a key paper a few years before that where he explained the basic idea. So halos mostly form along filaments. And so what's happening is that you get an anisotropic velocity tensor. And that's basically giving you the quote-unquote pressure that supports this. See, remember, the dark matter doesn't interact except gravitationally. So there's no bouncing. So with molecules, they're always bouncing off each other. And so you get, pressure, which by definition doesn't depend on direction. It's a scalar, not a vector. But with dark matter, your velocity tensor is complicated. And in particular, you get more velocity along the direction of infall. Other interesting case, if you actually look at the way the simulations evolve, they start with like beads on a string. The dark matter halos are thicker than the filaments. But then the filament quickly grows and becomes much thicker than the dark matter halos. And so the accretion becomes much more spherical. So halos are more elongated at small radius than large radius.
Okay. And would they also eventually circularize as the dark matter?
No, they do not circularize. No. What would cause them to do that? The thing that does, it doesn't circularize them, but it gives them an axis of symmetry, is the baryons. But that's only, remember, that's only like 10% of the radius of the halo. It can have an effect out to 20% or so. But on the large scale, the halo retains its shape.
Any other questions?
Incidentally, in the Bolshoi simulation outputs, we've got more than 30 columns for every single halo at every single redshift, 10 million halos at every redshift. And we tell you not only what the shape and the angular momentum are, we also tell you the orientation of the axes, and we do it at 2 different radii. Routinely available, publicly available. Use it.
Almost just addressed my question, which is what are the orientation of the dark matter filaments going into the galaxies? Are they coplanar? Do they tend towards some equilibrium?
They're pretty planar. But the really interesting question is, so what happens to the angular momentum of the gas? Because that's ultimately going to result in the angular momentum of the stars, although we can also see the gas. And it's a really interesting and complicated story. There's 4 different stages that occur at 4 different radii, starting with larger than the dark matter halo and going all the way down to the center. And there's a very detailed paper that we're about to submit. First author is Mark Danovich, D-A-N-O-V-I-C-H. Second author is Avishai Dekel, his PhD advisor. I'm, I think, the 4th author of that one. And it is an amazing story that I don't have time to tell you now, but just ask me at the coffee break. And look at the Danovich paper. It's an amazing paper. But that's the kind of stuff you can do with these high-res simulations. You take them apart, you really see what's happening.
All right. I think we can address some questions a little bit later.
Great.